Hello everyone, welcome back to our lecture on thermodynamics. So we are picking up with the topic of free energy. So Gibbs free energy, or simply free energy, which is how we'll refer to it from here on out, it is related to enthalpy and entropy. And the equation that we have is that G, which represents free energy, is equal to the system's enthalpy minus the absolute temperature times the entropy, S. Okay, so temperature, of course, is always going to be in Kelvin, just like it has been for our discussion on entropy. And just like enthalpy and entropy are state functions, free energy is as well. And so at constant temperature and pressure, we can rewrite this equation as the change in free energy equals the change in enthalpy minus the temperature in Kelvin times the change in entropy. So what free energy tells us is whether or not a reaction is spontaneous. So when delta G is negative or less than 0, we're going to have a spontaneous reaction. And of course, the opposite, if delta G is positive, then we're going to have a non-spontaneous process. So we remember from our discussion on entropy that an increase in disorder will favor a spontaneous process. And we can see that here in the equation, right? Because in front of that delta S value, we have a negative sign. And so we have negative T delta S. And so if delta S is positive, if we have an increase in disorder, that's going to help delta G be negative because of that negative sign in front of the variable of delta S. Okay, and also we know that exothermic reactions favor a spontaneous process. And so remember that exothermic reactions are going to have a negative delta H value, right? And so if delta H is negative, then again, that's going to help delta G be more negative and favor a spontaneous process. So just keep in mind exothermic reactions and an increase in disorder or a positive delta H value, positive delta S value, both of those are going to contribute to spontaneous processes. So let's take a moment to use that equation that we just saw for free energy, right? The change in free energy in terms of enthalpy and entropy, and calculate what that delta G value is. So in the question, we're given the enthalpy. The standard enthalpy is 100 kilojoules per mole, and the standard change in entropy is 250 joules per mole Kelvin. Is the reaction spontaneous at room temperature? So basically what they're asking, if a reaction is spontaneous, is they're asking, is delta G less than 0? Okay, is it negative? And at room temperature is going to be at 25 degrees Celsius. Okay, so we go back to that equation and remember that delta G is equal to delta H minus T delta S. And keep in mind that that temperature always has to be in Kelvin. So the first thing that we want to do is convert the temperature from 25 degrees Celsius into Kelvin. And we're going to go ahead and add that 273.15 to give us 298.15. Now, of course, only the 298 is significant because of the ones place from the temperature of 25 degrees Celsius. So we're going to make that 298.15, but that's not going to limit our sig figs anyways. Okay, now the big thing about when you're dealing with delta H and delta S values is that you have to notice that your enthalpy, delta H, is going to be in kilojoules, and your entropy, delta S, is going to be in joules. So you're constantly going to have to switch one of those two, and I think it's easiest to switch the delta S typically and look at delta G values in kilojoules. So we're going to take that delta S value of 250 joules per mole Kelvin and convert that into kilojoules. So of course 1 kilojoule is equal to 1,000 joules, and so we're going to divide by 1,000. Okay, and so our delta S value is actually 0.250. And now it's in kilojoules per mole Kelvin. Okay, so that's the first step with questions like this, is just to make sure that you have everything in the proper units. So our enthalpy and our entropy value, those units match, and we also have temperature in Kelvin. And so now we can start plugging it into that delta G equation. So delta G is going to be equal to our enthalpy, which is 100 kilojoules per mole. And that decimal does matter. That tells us that that 100 is 3 significant figures. And then subtract the temperature at 298 Kelvin times the entropy in kilojoules. So that's the 0.250 kilojoules per mole Kelvin. Okay, so our kelvins will cancel between the temperature and the entropy, and so now we know that we're going to get that delta G value back in kilojoules per mole. Now remember, because we are dealing with subtraction and multiplication at the same time, you want to do this step by step so that you can realize significance where it stops, whether it's the ones place or tenths place. So we have 100, and that stops at the ones place because of that decimal. And then we subtract the two values here. When you multiply those two values, the least number of sig figs is 3 sig figs from the entropy value, and so we get 74.5. Okay, so this goes out to the tenths place, and the shortest is the ones place. So we're going to report our final value out to the ones place, and our units are still in kilojoules per mole. And so delta G will be equal to 25 kilojoules per mole. Okay, so notice how those sig figs, they constantly change when we're using those subtraction rules. It's no longer about the number of significant figures. Okay, so is this reaction spontaneous? And again, remember, we're asking, is delta G negative? And it's not. So this is considered a non-spontaneous reaction. Okay, and if they are asking about what temperature conditions will it become spontaneous? So let's stop here for a second and just look at our delta H and delta S values to see which of the two is favorable. And then we'll answer this question. So when we look at the delta H value, notice how it's a positive value. Okay, and if we have a positive delta H, remember that that is an endothermic reaction. Okay, and so that is going to be unfavorable. That's not going to help make this reaction spontaneous. Now the delta S value, our entropy, that is also positive. But when we have an increase in entropy, right, so we have a positive delta S, that is an increase in disorder. And that is favorable to a spontaneous reaction. So basically what we want to do is we want to increase how much that entropy is contributing to our delta G value. So the way that we're going to do that, if we look at that equation, right, we've got temperature times that entropy. So if we want to increase that portion, we're going to have to increase the temperature. And what we're going to do is we're basically going to say, okay, we need delta G to be either equal to or less than 0. And so let's erase what we've got here so far. and keep that delta G equation. All right, so we need delta G to be less than or equal to 0. And so if we set that up, that means that the equation that we have, delta H minus Ts, that needs to be less than or equal to 0. Right, okay, so we're basically going to solve for the temperature at which the delta G value is equal to 0. And so if we rearrange this equation, right, you've got delta H minus T times delta S less than or equal to 0. Move that T delta S over to the other side and divide by delta S. You should get your enthalpy, your change in enthalpy divided by your change in entropy should be less than or equal to your value of T. Okay, and we know what the change in enthalpy and the change in entropy are, so we can plug those in, again, making sure to use the entropy that is in kilojoules. So we have 100 kilojoules per mole for our enthalpy, divided by the 0.250 kilojoules per mole Kelvin. Right, so the kilojoules and the moles, they'll cancel out, and 1 over Kelvin will give us the temperature in Kelvin. And so that needs to be less than or equal to T. And divide those out, you should get 400. Okay, so the temperature needs to be greater than or equal to 400. And we can rewrite this if you want to just flip it around and basically say temperature is greater than or equal to 400 Kelvin. Right, and if you want to look at that in degrees Celsius, of course, subtract out your 273. And so you get temperature is greater than or equal to 127 degrees Celsius. And so, of course, that's going to be much higher than room temperature at 25 degrees Celsius. And that's because, again, we want to favor that positive delta S, that increase in disorder, and drop down the significance of that delta H value that's unfavorable in comparison. Okay, so just like with entropy and enthalpy, we've seen this equation before where we use the standard free energy of formation before it was the standard entropy of formation values. These are what we get from a table in your textbook, right? So we can use these formation values, take the sum of the products minus the sum of the reactants, and find the standard free energy of a reaction. Okay, and also keep in mind, just like for enthalpy back in the past, delta G formation will be 0 if you have elemental substances in their standard states. So if you can't find a delta G value in a table, or if it's not given to you on a test, chances are it's 0 because it is an elemental substance in its standard state. Okay, so we're going to run through an example. We've seen this plenty of times. We are going to take the sum of the products minus the sum of the reactants. Okay, and so of course we have to multiply them by the coefficient in front of each substance, and the only one that has a coefficient here is the first reactant in the list. So we're going to start by adding together the two products. Right, so we need lithium carbonate, so that's here, and we are looking for the free energy change, so we're focused on the delta G values. Okay, so we need that negative 1132.19. I'm going to ignore the units until the end because it's all in kilojoules per mole. We don't really need to worry about what those are. So we have got negative 1132 added to the free energy change for water in its gaseous state. Again, make sure that you are focused on that phase and that it is a gas and not a liquid. So we're going to take that negative 228.59. Okay, and then subtract out our two reactants. Again, making sure to multiply that first reactant by 2 for the coefficient, and then find lithium hydroxide. And so that's negative 441.5. And then add that to our other reactant of carbon dioxide gas, okay, of negative 394.36. Okay, so again, very important that you take this one step at a time so that you can keep up with significant figures because we've got multiplication and addition and subtraction going on. So the first two values, when you add those up, they both go out to the hundredths place, and so your significance will go out to the hundredths place as well. And so we get negative 1360.78, and again, it is significant out to that 8. Okay, and then we subtract the other two. Now again, multiply those first two values here and check, just because that may go up into the thousands, and so it could change your significance. But this time we get negative 883.0, and so that does go out to the tenths place because of 4 significant figures, right? So 4 sig figs there, and so we need 4 sig figs here as well. Okay, and then add that to our negative 394.36. Okay, and so that first value is going to limit our significance out to the tenths place, and so when we add those two values together, and you get the negative 1277.36, it's only significant out to the 3, out to the tenths place. Okay, and then we've still got that negative 1360.78. Okay, and so when we're subtracting those two, that means that it should go out to the tenths place for our final answer, and you are subtracting a negative, so that becomes plus a positive, and overall you get a delta G value that's equal to negative 83.4 out to the tenths place, and that is in kilojoules or potentially kilojoules per mole, depending on what they're asking for on the units. And they're asking whether it's spontaneous or non-spontaneous. Again, all that matters is the sign. So because delta G is negative, that indicates that we have a spontaneous reaction under these conditions. Okay, so now we're going to look at temperature dependence of the free energy change. And we've kind of seen this a little bit, but if you only have two variables, you have your delta H and your delta S, ignoring temperature for a moment, you have two variables that can be changed, and you have a positive and a negative sign, right? So you have a total of 4 possibilities. Either your enthalpy and your entropy can both be positive, both be negative, or one be positive and one be negative. So we're going to look at each of these 4 cases, right? And the first one is if both are positive. So remember, if delta H is positive, your enthalpy, you have an endothermic process. And so remember that that is unfavorable for a spontaneous reaction. Okay, so if delta H is positive, that's unfavorable. But delta S positive, that is favorable, right? An increase in entropy is going to be favorable. And so you've got this kind of juxtaposition between the two where one is favored and one is not favoring. So what you want to do is increase that variable between temperature and entropy. And so if you increase the temperature, you're going to increase that T delta S part of the equation, and so you'll get a spontaneous reaction. So if you have an endothermic process with an increase in entropy in the system, it's going to be spontaneous at high temperatures. Okay, and then opposite, if we have delta H and delta S negative, then remember enthalpy is going to represent an exothermic process if it's negative, and that's going to favor a spontaneous reaction. But if delta S is negative, you have a decrease in the entropy of the system, and so that's unfavorable. Right, so again, kind of opposite here. This time you need the entropy to be less significant in the equation. And so we need that delta T, or sorry, that temperature times delta S to be less than your enthalpy. And the way we're going to do that is lower the temperature, right? So spontaneous at low temperatures. Okay, and now we have the last two. So if delta H is positive, we're looking at an endothermic reaction. Remember, endothermic reactions are unfavorable for spontaneity. And delta S is negative, that's also unfavorable. So if neither option is favorable, then it's not going to matter how much you increase or decrease that temperature. It's going to be non-spontaneous at all temperatures because both enthalpy and entropy are unfavorable for a spontaneous reaction. And then the last one, we've got delta H is negative and delta S is positive. So this time you have an exothermic process, that's favorable, and you have an increase in the entropy in the system. So both parts are favorable, and so it should be spontaneous at all temperatures. Okay, so this table just summarizes what we've said. Again, exothermic reactions are going to be favorable as well as an increase in entropy. And so if you have both at the same time, you'll always have a spontaneous process. And then opposite, if you have an endothermic reaction with a decrease in entropy, you're never going to have a spontaneous process. Okay, so let's look at an example. We have popular chemical hand warmers generate heat by the following equation. How does the spontaneity of this process depend upon the temperature? So if we're generating heat, remember that that is going to be an exothermic process, right? When we hear the production of heat, that is exothermic, and so we've got a negative delta H value. And remember that that is favorable, right, for a spontaneous process. And then to look at entropy, remember we've got to go back and look at the reaction and what's happening to our molecules. And the most important thing are phase changes, right? So gas is going to be the most disorder and solids are going to be the least disorder. And so if we look at the total moles of gas on the reactant and the product side, we have 3 moles of gas on the reactant side. And we don't have any on the product side, right? Because everything becomes a solid, so 0 moles of gas. Okay, so what's happening here is that you're having a decrease in entropy. You're lowering the disorder of the system. And so you have a negative delta S, and remember that that is unfavorable. Okay, and so if we have that delta G equation equals the enthalpy minus the temperature times the change in entropy, this portion is unfavorable, and so if we want to make that less significant, we need to decrease that temperature. So it's going to be spontaneous at low temperatures. All right, and if we go back, of course, and just review that table, we can see that if we have an exothermic reaction with a negative delta S value, it's going to be spontaneous at low temperatures. All right, so notice how I put low in parentheses, right? Because that term is relative when we talk about high or low temperatures. It's within respect to what exactly. So we need a reference temperature to tell us whether a temperature value is considered high or low. And the way that we determine this reference temperature is by setting that delta G value, that free energy, to 0. Because remember, if we set the free energy to 0, then we're looking at a system at equilibrium. And so, of course, if you look over here to the right, we've got the non-spontaneous versus the spontaneous process. So if delta G is greater than 0, remember that you have a non-spontaneous process. Delta G less than 0, we have a spontaneous process. And so you can see the easy ones that we talked about, where if you have an endothermic reaction, right, delta H is positive, and you have a decrease in the entropy, then both of those are unfavorable, and it doesn't matter what you do, it's always going to be non-spontaneous. And so you can see that red line, it's never going to cross over free energy at equilibrium. Okay, and then opposite, right? If we have an exothermic process, a negative delta H value, as well as an increase in entropy, a positive S, then that's always going to be spontaneous. But if we look at the situation that we just had, where we have an exothermic, so a negative delta H, as well as a negative delta S value, right? So if both are negative, that's this line here. We can see that that line crosses where delta G is equal to 0. Okay, and so if we have a low temperature, right, as the temperature, because increasing temperature is here on the x-axis, so at low temperatures, you'll see that we're spontaneous, right? And then as you get too high in your temperature, so if we look at a high temperature way out here, we can see that we've reached the realm of non-spontaneous. Okay, and so how to determine if you have a low temperature is right at delta G equals 0. And so if we set delta G equal to 0, we find that the temperature, the reference temperature that we're looking for, is going to be the change in enthalpy over the change in entropy. So let's look at a calculation of that reference temperature. Estimate the boiling point of carbon disulfide. So when we're talking about a boiling point, just remember that that is when we have carbon disulfide as a liquid, and it is interchanging between a liquid and a gas. And so we heard back in the phase change section how when you're at a phase change, you're technically at equilibrium. And you're at equilibrium between the two phases. You have both liquid and gas occurring at the same time. So if we want to estimate the boiling point, we are trying to estimate that temperature at equilibrium. And so we get back to that equation. Remember, temperature is equal to the change in enthalpy over the change in entropy. And so we're going to need to calculate delta H of this reaction that we have divided by the delta S of that reaction. Okay, and so we've done this previously, where if you calculate delta H of a reaction using the enthalpy of formation values, it's going to be products minus reactants. So we're going to take the gas, which is the product, and looking at those enthalpy values, you get a value of 116.9, and then subtract out that the enthalpy for the liquid, so 89.70, and the shortest decimal place is out to the tenths place, and all of those are in kilojoules. We're going to ignore the per mole part because the entropy values are also in per mole. So those moles will cancel, and we're focused mostly on the kilojoules. Okay, so enthalpy of reaction, you should get 27.2 kilojoules. Okay, and then we're going to do the same thing for the change in entropy of the reaction. Again, starting out with that gas, which is your product. So that's 238 minus the 151.34. Okay, and that's in units of joules per Kelvin. Okay, subtracting those, again, the importance is out to the tenths place, but we will keep it out to the hundredths to prevent round off error. We didn't have to do that with the first value because it just ended with 27.2. So we get 86.6 and then 6 subscripted, not significant, joules per Kelvin. And of course, the issue is anytime we're dealing with enthalpy and entropy at the same time, those units typically are not going to match, and so we're going to have to convert one of them, and preferably that entropy value, into kilojoules by taking 1 kilojoule over 1,000 joules. Okay, so of course we're moving that decimal place over 3 places to the left, and we get 0.0866 and then a subscripted 6 kilojoules per Kelvin. And now we can plug those into our temperature equation, where the temperature of the boiling point, or the temperature at equilibrium, is going to be the enthalpy value, 27.2 kilojoules, divided by the entropy value in kilojoules of 0.0866, subscripted 6 kilojoules per Kelvin. Okay, so kilojoules cancel. Of course, 1 over Kelvin will bring us back up to Kelvin, and 3 significant figures will give you 314 Kelvin. And of course, if we want that in Celsius, we subtract the 273, and it's out to the ones place, and so you get 41 degrees Celsius. Okay, so just depending on whether they want it in Kelvin or Celsius there. Okay, we're going to move on to a topic of free energy and equilibrium. So before we get too far into this, we want to talk a little bit about equilibrium. Now we'll talk about equilibrium in more depth in a different video. But we want to briefly bring up the definitions of Q and K so that we can use those in the free energy equation that we'll look at later. So when you see this variable Q, just know that it is the reaction quotient. And so when we are calculating the reaction quotient Q for a given reaction, then we need to look at whether they're giving us values in molarity or values in partial pressure. So if they're giving values in molarity or concentration, then we're going to take those concentrations and raise them to the power of the coefficient in that reaction. So notice how the coefficient of Cx, we're raising that to the power of x. And it's always going to be products over reactants. Okay, so products over reactants there. And raising everything to the power of their coefficients. Now, if we're using partial pressures, it's as simple as swapping out those molarity, those concentrations, with partial pressures. So same exact equation, you raise it to the power of the coefficient. You just swap out whether it is molarity or whether it's partial pressures. Now, regardless of whether you're calculating Q or K values, we're going to disregard any units. Okay, so you're not going to use units when calculating these values. And the only difference between Q and K is that K is specifically at equilibrium. Okay, so Q can be at any point in a reaction, whether you're at equilibrium or not. K is a constant value specifically at equilibrium, but the calculation is the same, whether you're calculating Q or K. So let's look at some initial concentrations or pressures and calculate that reaction quotient Q. So in this first example, we have the molar concentrations for our reactants and our products. So the first thing that we want to do is set up that equation for Q. And remember, it's going to be our products, right? And it's going to be in concentration values. So the concentration of nitrogen gas. And we don't have to raise that to a power because the coefficient there is assumed to be 1. And then multiply that by the concentration of hydrogen gas. And we do want to raise that to the power of 3 from the coefficient 3. And then divide by your one reactant, ammonia NH3, and raise it to the power of 2 from that coefficient. Okay, so we can plug in the molar concentrations that were given. For the nitrogen gas, that's 1 molarity. And remember, we can ignore the units because our values for Q and K are going to be unitless. And hydrogen gas, also 1 molarity, raise that to the 3rd power. Okay, so we're basically doing 1 to the 4th power overall, divided by ammonia, which is 0.2, and raise that to the 2nd power. Okay, and plug that in, you should get a value of 25. So Q equals 25 for that first example. Now, in the second example, we can rewrite this equation, but it's going to look basically the same. You're looking at partial pressures, so it's going to be the partial pressure of the nitrogen gas times the partial pressure of hydrogen gas raised to the 3rd power, divided by the partial pressure of ammonia raised to the 2nd power. Okay, and so again, we're going to plug in those partial pressures, ignoring units. And so the partial pressure of nitrogen gas is 2. And then times the partial pressure of hydrogen gas, that's 1 to the 3rd power, which is just 1. And then divided by your partial pressure of ammonia, which is basically 3 squared, or 9. And you should get back a value of 0.22. Okay, again, 2 sig figs because, of course, 2 sig figs in our values here. Okay, so that was a brief introduction to the reaction quotient and to the equilibrium constant. And knowing those values of Q or K, we can calculate the free energy change. So if we're looking at a free energy change that's not at standard conditions, we will find that it is equal to the free energy at standard conditions plus RT times the ln of Q, right, the natural log. So R is the gas constant. Again, we're going to use that 8.314 because it is in joules per Kelvin times mole. Those are the units that we need. Temperature has to be in Kelvin, and then the reaction quotient Q, that could be calculated either from molar concentrations or partial pressures, right? Because it's just going to be a ratio at the end of it. So let's calculate the free energy change for the following reaction at 875 degrees Celsius. And they give us the partial pressure of all gases. That's going to be 1.88 atmosphere. And they give us the free energy change at standard conditions is 33.0 kilojoules per mole. So here we can use that equation delta G equals delta G standard plus RT times the ln of Q. Okay, so let's focus on that RT ln of Q phrase there for a second. Now the issue that you're going to run into is if we look at the delta G value, notice how it's in kilojoules. But our R value of 8.314 is in joules per mole Kelvin. So of course, again, you have this difference between joules and kilojoules, and so we're going to have to convert everything into kilojoules. Let's go ahead and do that now. Okay, so our R value needs to be in kilojoules. So again, divide by 1,000. All right, so R divided by 1,000, move that decimal place to the left 3 places, you get 0.008314, and now it's in kilojoules per mole Kelvin. And then the temperature value, of course, notice from that R constant that temperature needs to be in Kelvin. So we will take that and add the 273. So 875 plus 273 gives us a total of 1,148 Kelvin. And that's plenty of sig figs, so that's why I'm not adding that 0.15. Okay, and now we need to find out what the value of Q is at the conditions given, right? So we've already seen this equation for Q for this reaction, and because we're dealing with partial pressures, then it's going to be the partial pressure of the nitrogen gas times the partial pressure of the hydrogen gas raised to the third power, divided by the partial pressure of ammonia raised to the second power. And all of them are 1.88, so that makes it convenient, right? We're going to have 1.88 and then times 1.88 to the third and divided by 1.88 raised to the second power. Now you can plug this all into your calculator if you'd like. You can do a little bit of power magic, right? So this becomes 1.88 raised to the fourth power divided by 1.88 raised to the second power. So of course those will kind of cancel out until you're down to 1.88 squared. Okay, or you can plug it all into your calculator, but we should get back, let's see, 3.53. We want at least 4 digits for significance because we had 3 carry an extra, and so 3.53 subscripted 4. No units there. Okay, so now we have changed the units for R and T and calculated our Q value. So now we can finally plug things into our original equation where delta G is equal to the delta G standard that they give us of 33.0 kilojoules per mole. Okay, and then add the R value, 0.008314, and that's in kilojoules per mole Kelvin. Okay, times our temperature of 1,148 Kelvin. So our Kelvin will cancel. Now we've got both in kilojoules per mole, and then times the natural log of that 3.534. Okay, now if we go ahead and multiply everything out, our RT and natural log of Q, then delta G is equal to the 33.0 plus 12.04 and 12.049. Keeping an extra digit until we're done, and all of that is in kilojoules per mole. Okay, and so our delta G, of course, when we're adding the values, it's based on the shortest decimal place, and so of course that's coming from our 33.0, and so out to the tenths place is 45.0 kilojoules per mole. And so they ask, is this reaction spontaneous under these conditions? And of course, delta G is positive. That is what tells us whether it's spontaneous or not. And so this is a non-spontaneous reaction at the conditions given. Okay, now if we are at equilibrium, right, then we have learned that the free energy equals 0. So if we go back to the equation that involves the reaction quotient, if delta G here is equal to 0, then we can rearrange the equation and get that the standard molar entropy is equal to negative RT, and because we're at equilibrium, remember that it becomes a K instead of a Q. The K just tells us that we are specifically at equilibrium. Okay, and so that's how we're getting this equation here, right? If Q equals K, we're at equilibrium, delta G equals 0, and so the standard free energy is going to be equal to negative RT times the natural log of K. And so that tells us a few things about what our value of K is and what that tells us about delta G. So if we have a very large K value, right, if K is greater than 1, then we have a standard molar entropy, or sorry, a standard free energy value that is negative. If K is less than 1, so if K is very small, then you get a change in standard free energy that is greater than 0. If K is greater than 1, you're going to have products that are in more abundance. And again, remember that your Q values or your K values, those are always equal to products over reactants. So of course, if you have a very large K value, that means you have more products than you have reactants at equilibrium. And vice versa, if K is very small, then that means you have a large amount of reactants compared to your products. Okay, so this should be our last example for this topic. Calculate the equilibrium constant for the dissociation of dinitrogen tetraoxide at 25 degrees Celsius. And so if they're asking about that equilibrium constant, remember that's going to be the equation we just saw. Delta G standard is equal to your negative RT times the natural log of that equilibrium constant K. Okay, so if we are solving for this reaction, we first need to figure out what delta G standard is for this reaction. And so we're, of course, going to need those delta G of formation values for our products and our reactants. So delta G of the reaction, it's always going to be products minus reactants, and that product has a coefficient of 2. So 2 times the free energy of formation for the nitrogen dioxide. Okay, so that's the 51.30. And I'm going to ignore units for now just because all of it's going to be in kilojoules per mole. So products minus the reactant dinitrogen tetraoxide of 99.8. And of course that goes out to the tenths place. And we get back 2.8 kilojoules per mole. Okay, so we have our delta G value. Of course, R, again, because that delta G is in kilojoules, R also has to be in kilojoules. And so we've already found that R in kilojoules is 0.008314. and kilojoules per mole Kelvin. And so, of course, that Kelvin means that we need to also change the temperature into Kelvin by adding 273 to that 25. And so at room temperature, you have 298 Kelvin. Okay, so we've fixed all of our units. And now looking at this reaction, if we want to solve for K, we need to divide both sides by negative RT, right? So the ln of K, or the natural log of K, will be equal to your delta G value of 2.8 kilojoules per mole, and divided by a negative RT, so we'll just throw this negative up front, times the 0.008314 kilojoules per mole Kelvin, and times the temperature value of 298 Kelvin. Okay, so our units of Kelvin will cancel. So will all the kilojoules per mole, right? Because at the end of the day, K is a unitless value. So all the units have canceled, but I kept them so that I knew to match up the units for R, T, and delta G. Okay, so again, all of this will be out to at least 2 digits of significance, and we get back negative 1.13. and that is equal to your natural log of K. And so if you want to solve for K, remember the opposite of the natural log is to raise everything to the power of e, to your exponential function. And so e and the natural log will cancel, and you've got K equals the exponential function raised to negative 1.13, and that comes out to be roughly 0.32. Okay, so that ends this topic and the end of the thermodynamics lectures.